This is the chain reactions unit, video 2. So in this one, we can talk about something sort of fun, nuclear weapons. As soon as it was discovered that the neutron-induced fission creates more neutrons, it was clear that there was a potential method for releasing enormous nuclear energy. So this concept of a nuclear chain reaction had actually been patented in England by a nuclear physicist, Leo Szilard, in 1932. The first actual chain reaction, though, was achieved by a team led by Enrico Fermi at the University of Chicago in 1942. So what they found was that if those neutrons can be made to hit other uranium nuclei, then soon the doubling will result in fission of nearly every nucleus. And that it usually only took about 80 doublings. So that's kind of remarkable in many ways that it only takes about 80 doublings, and that each of these doublings takes so little amount of time that it goes through all 80 doublings very, very, very quickly, releasing that energy very, very quickly. However, in order to have this, we need to have something called a critical mass. So if the uranium chain reaction is to work, there needs to be enough material so that the emitted neutron hits another uranium nucleus. So instead of maybe like escaping between the nucleus, remember that in an atom, about 99% of the volume of an atom is empty space. So those uraniums have to be packed in there pretty tightly, and we want to make sure that the neutron just doesn't escape to like the electron cloud or something like that. So we need to have enough uranium surrounding that initial one so that once those neutrons are released, they can hit other uranium atoms. So if enough uranium surrounds the initial fission so that the neutrons will not escape, then we have something called the critical mass. There were 3 types of nuclear weapons. So first off, we had the uranium one. This is the one that destroyed Hiroshima. During World War II. Some interesting facts. It was never tested. It's very hard to get uranium. So they didn't have very much of the material. So they didn't feel that that it was well, first off, it was a very simple design. So they felt that it was so simple that they didn't need to test it because they thought that might be a waste of materials. So for this one, it's this type of bomb. It's easy to build, but hard to get materials. The next type is the plutonium one. This is the one that was dropped over Nagasaki. So first off, plutonium is kind of easy to get. much, well, relatively speaking, it's a lot easier to get plutonium than it is to get uranium. Um, so for this one, it has to be an implosion bomb. That makes it hard to build. Um, and as far as we know, it kind of takes the resources of a full country to build. So, in terms of terrorism, we don't really worry about terrorists getting a uranium bomb because it's so hard to get the materials. We don't worry about terrorists getting a plutonium bomb because uh, terrorists usually work in small cells. They don't have the resources to make one of these. However, countries like North Korea, we do worry about them making a plutonium bomb, um, and there's evidence that they may have started to build one. The next type has never been used in war, luckily. This one is the thermonuclear, or the hydrogen bomb, or the H bomb. So, how this one does is it uses the heat from a plutonium or uranium bomb to fuse the molecules of deuterium and tritium. Keep forgetting my eyes. So this is a fusion bomb. Remember that deuterium and tritium are two isotopes of hydrogen. So that's really where this comes into. Now, there are a lot of difficulties to build one of these. It's very, very, very difficult to build a hydrogen bomb. Um, and it basically comes in three stages. We have the fission bomb, which generates heat. That heat has enough energy to push the deuterium and tritium together, and then the fusion energy released in that makes it an even larger explosion. So for these ones made extremely, extremely large explosions. But again, fortunately, um, they've never been used in warfare. Now, a more peaceful application for nuclear energy is for a nuclear reactor. So, a nuclear reactor is a device which has a sustained chain reaction that takes place. It does not involve the doubling. Instead, from each fission, only one of the emitted neutrons hits another nucleus to cause another fission. Um, so it's kind of like, if every couple had on average 2 children, then the population would not grow. The power output from a sustained nuclear reaction does not grow, but it's constant. So it's something where we're trying to harness the chain reaction. So here is kind of like a picture of what's going on. It's important to realize that the actual nuclear reactor in a nuclear power plant is pretty small. Here it is. Its only purpose is to generate heat. Heat from that is then used to boil water, which we get steam. The steam travels and then blows across turbines and then comes back and then gets condensed into water where it's then reheated back into steam and everything else. Um, the real danger, though, is that we pressurize these, so the steam is very it has a very high pressure, and the water is high pressured as well. So what happens is if there's a break, that steam will instantly, remember that a gas has 1,000 times the volume of a liquid or solid. So what happens is we get a flash explosion or a steam explosion, and that steam fills out 1,000 times the volume. So here's where we have our containment building. The containment building has to be so much larger than everything else because it's trying to capture in case there's a steam explosion. Now, these classic huge towers that we always see, it's important to realize that those are not radioactive. You see, we use water to cool these steams to help condense the steam back into water, and then these big towers are used to cool off that hot water. So what you see coming out of those towers is plain old water vapor. So for use in a bomb, the uranium-235 has to be enriched to about 80%. You see, there's two isotopes of uranium that we mine. We got our uranium-235, which is like our the kind we use to make bombs and whatnot. But then there's also uranium-238. So if you were to dig some uranium out of the ground, about 99.9% of that will be uranium-238, which does absolutely nothing. It's completely inert. And about 0.1% of that, maybe more, maybe less, will be uranium-235. So we have to separate those two isotopes, and that's a process which we call enrichment. So for a bomb, the uranium-235 has to be enriched to about 80%. So 80% of the atoms are 235, 20% of the atoms are 238. However, for a nuclear reactor, it only needs to be enriched to 3%. So only 3% of those atoms are 235, 97% of those atoms are 238. Additionally, the reactor uses slow-moving neutrons, while the bombs use fast-moving neutrons. So what I'm getting at here is that we do not have to worry about a nuclear power plant becoming a nuclear bomb. The fuel is not enriched to a sufficient level to make it into a bomb. So it's just something that it's important to remember and to realize. All right, I'm going to conclude the video here. In the next video, we'll take a look at some different designs for nuclear reactors.